together session sponsored by the Brosis Foundation. We're very proud and very pleased to make these tutorials available week after week, both in English and in math. And we are convinced that there are some people who are going to benefit each week. This might not be your week, but I promise you that there will be some weeks that you'll find stuff that you will benefit from. Today, we're going to take our research into inequalities a step further. Just to remind you of what we did in the previous session, we were able to graph an inequality in two variables. We did ones in one variable. We also did others in two variables. For example, if we had y, say, greater than 2x minus 3, and we were asked to graph that. Well, what we recommended was that you look for the border, because this is going to be an area. There's going to be a line separating the section that fits from the section that does not fit. So there'll be an area that satisfies this condition, and then on the other side of the line is an area that does not satisfy this condition. So the way we approach this is to find the border. And the border is obtained by graphing the line y equal to 2x minus 3. Okay, and there are several ways to graph the line. We can get points, get 3 points by just making a table, an XY table, and get 3 points, plot the points and connect them. Or we can use other methods. For example, I like to use the slope and the y-intercept. I like to do that. You can use whatever method works for you. You can make a table, for example, your XY table, and you could choose numbers like, say, for example, 0, 1, and 2. When x is 0, y is negative 3. When x is 1, y is negative 1. When x is 2, y is 1. If you plot those 3 points and take a straight edge and pass a line through the 3 points, there is your line. Okay? I don't have time for that. I look at this and I know the y-intercept is negative 3. So I say, okay, here's your x-axis, here's your y-axis. This is negative 3. I'm just doing a sketch, so it's not a big deal. Then the slope is 2, which means if I go across 1 unit, then according to this, the graph is going to go up 2 units. That's why the slope is positive 2. So now I know that the graph passes through these 2 points, and there will be only one line that passes through 2 points. Only one line, okay? So I can now connect these 2 points and extend both sides. Now it says that it's greater than, it is strictly greater than, so from our session last time, we discovered that if it is strictly greater than or strictly less than, we use a dotted line. Whereas if we saw the greater than or equal to or less than or equal to, we would use a solid line. So we use dotted line if it is strictly greater than or strictly less than. But if it is less than or equal to or greater than or equal to, we use solid line. So in this case, we're definitely using a dotted line. Here we go. Again, it's just a sketch. Okay, and it's good to label your boundary. And that's the boundary y equal to 2x minus 3. That's your boundary. Now, the next thing to do is to decide, am I shading above the line or below the line? Are my solutions above the line or below? Or is the solution set above the line or below? Well, let's check it out. It says y is greater than these values. On the line is where y is equal to this value. So if it is greater than, it has to be above. Greater means above. So therefore, my solution set would be all points in this shaded area. Okay, and that would be the answer to that sample. That's what we did last session. Today, we're going to take it up a notch. We're going to find the solution set for systems of inequalities. And I'm hoping that at the end, we can do, where you see this word plus, you can do an example that involves what is called linear programming. That is trying to find the maximum or the minimum for a certain set of criteria, okay? So that's a goal for today. So let's go. Okay, so whenever you see a system of inequalities, a system means that there are multiple conditions. So you have 1, 2, you could have multiple, you could have 2 conditions, you could have 3, 4, 5. Okay? Today we're going to just focus, for the most part, on just 2 different set of inequalities. For example, if we're asked to graph x greater than, sorry, I need to put my glasses on so I can make sure I copy down the question properly. So it's not x, but rather y greater than x plus 2 and y less than or equal to negative x plus 1. They like to put the curly brackets to show that these 2 inequalities go together. So you want one common area that satisfies this and satisfies that. Okay, so before we had one inequality and that was all. Now you're having 2 inequalities and find the area that fits both conditions. Got it? Okay, so technically we're going to end up with 2 graphs on the same XY coordinates. Okay, so here we go. Y is greater than x plus 2. So as I look at this, I know that the y-intercept is positive 2 and the slope is positive 1. So if I go to positive 2, okay, I go across 1, it's going to go up 1. So these will be 2 points on the first graph. The first graph says that it's greater than, so it is a dotted line. So it's going to look something like this. This is the graph y equal to x plus 2. So that's my first graph. We'll deal with the shade afterwards. Let's draw the graphs first, then we'll shade after. So the second one says that y is less than or equal to negative x plus 1. So in this case, the y-intercept is 1. So this is the y-intercept, and the slope is negative 1, which means that I go across 1 and I come down 1. So therefore, I'm going to be here. Okay? So again, this one is less than or equal to, so now we're talking about a solid line, solid. So we're going to have a graph going this way, and it's going to cut this one right here. So if you were doing it, you would have a ruler, and you'd use a ruler to extend your line. Okay? So now we are ready to find the common area. So these are two boundaries, and now we need to find what area is common to both. Now, there are two ways to do this. There's some who shade for the first one, so it's greater than, so they would shade all above this dotted line. And then the next one says less than, then they will shade all below this solid line. So I prefer to shade only the area that satisfies both. So we need, it's above this and it's below this, so it's actually this area in this section right here. So it's actually this. So that's the solution to this particular question. Y greater than x plus 2, so it's above. And y less than or equal to this one, so it's below. So it will be below. And the area that they overlap, the overlapping area is in this corner right here. Okay? Make sense? Let's try another one to bring it home. Okay. Negative 3x plus y is less than 3. And x plus y is greater than negative 1. Okay? So negative 3x plus y is less than 3, and x plus y is greater than negative 1. So the first thing that I'll do is I'll rewrite the inequalities so that I have y by itself. So for this one, we have to move this over to this side, so we end up with y is less than 3x plus 3. All I did was move this over to the other side by adding 3x to both sides. So y is less than 3x plus 3, or 3 plus 3x, the same thing. For this one, I'm going to have to subtract x so that I'm left with just y alone. So I end up with y greater than negative x minus 1. When I subtract x, it becomes a negative x over that side. So now, these will be my boundary, y equal to 3x plus 3, and also y equal to negative x minus 1. Let's see what that looks like. Okay, so here, the y-intercept is 3, positive 3. Here, the y-intercept is negative 1. Okay, so here's 1 point. And according to this, the slope is 3. So if I go across 1, I will have to go up 3. That's what the slope is. So if we call this 1, we go across 1, and we're up 3. Okay, and this is less than, so we're gonna, and it's strictly less than, so it's a dotted line. So I'm going to draw something that looks like this. Okay. And this is the boundary y equal to 3x plus 3. That's one boundary. And now we need to do the other one. This is a negative slope. So this is -1, intercept is -1, so this is -1, and slope is -1 means that you go across 1 and you go down 1. Again, this one is a dotted line. So we go okay, and this one is going to be the boundary y equal to -x minus 1. So now we need to decide where on this graph is the solution set. What is the common area for both inequalities? Well, the first one says that it's less than, okay? So that means this is your line here. Less than means that it's below our line, below the line. This one says greater than, so this one is have to be above this line right here. So where do we have below this one and above this one? It seems to me that I'm in this corner right here. So that would be our solution set. So this is how you graph systems of inequality. And if you are given 3 inequalities, you just graph the 3 and find the common area. So let's do one like that. And then we transition over into linear programming, which is a very, very engaging set of circumstances. Okay, so here we go. Okay, so in this case, I'm giving us 3 sets of limits, 3 sets of limits. X must be greater than or equal to 0. Y must be greater than or equal to 0. And then y must be less than -x plus 4. And y plus 3 must be greater than or equal to 2x. So this one, I can rewrite this as y is greater than or equal to 2x minus 3. Okay? So we're going to have something to this effect. This tells me that I'm working in the first quadrant only. I don't care about when x is negative. I don't care about when y is negative. So I can arrange my graph so that I'm using up mostly this first quadrant. Here, x is positive, x is positive, y is positive. Over here, x is negative, y is positive. Down here, x is negative, y is negative. Over here, x is positive, y is negative. So this is the corner that we're going to be concentrating on. So x greater than or equal to 0 will be everything from here to infinity. Y greater than or is equal to 0, everything from here to infinity. So this is where we're working with. Now we need to get to this one. Y equal to negative x plus 4 is our boundary. So if we use, say, 4, we could go so this is negative 2, 2. Okay, here we go. So the first one, the y-intercept is 4. When x is 0, y is 4. And then the slope is negative 1, which means that if I go across 1, it's going to go down 1, so it's going to go down to 3. And what type of line do we have? We have a dotted line, So let me see if I can get this drawn. Okay, so this, and now I can label this as y equal to negative x plus 4. This is our x-axis. This is our y-axis. And if we look at this, we realize that we're going to be shading below this line, but we leave that for later. This one says y is greater than or equal to 2x minus 3. So this is negative 3 is our starting point. We go across 1 and we go up 2. Y equals 2x minus 3. So negative 3 is the y-intercept. Your slope is 2. You go up, you go across 1, up 2. And now this is a solid line. So I'm going to draw a solid line that goes across from here. Okay, so this is our solid line, and this is the line y equal to 2x minus 3. So here we go. What is the common area that satisfies all 4 limits, all 4 conditions, all 4 inequalities? Well, it has to be above this line, it has to be to the right of this line, it has to be below this line, and it has to be above. This one, it says greater than or equal to, so it has to be above. So when you look at this, it's actually that would be your solution set. That space that is right, it says 1, 2, 3, this 4-sided figure, that quadrilateral, that 4-sided figure. Okay, so now we're basically finished with just drawing systems of inequalities. And now I want to show you a real world application of this concept. Okay, many times in businesses, you have different variables, different things. Like for example, if you're running, say, a franchise, say a Kentucky Fried Chicken franchise, you want to maximize the number of staff. You don't want to employ too many members of staff. You don't want to have too little. You don't want to overextend yourself in terms of inventory. You don't want to buy too much, so you have a lot in storage, but then you don't want to buy too little. So there comes a point where you have to know how to balance what amount is the right amount. what is the maximum, what is the minimum, those type of things. If you want to minimize your expenses, you want to know what type of combination will give me the minimum, et cetera, et cetera, et cetera. So that's where we come into what is called linear programming or optimization. So it's linear programming. It's also referred to as optimization. Okay, so we're going to look at an example like that. Okay, so I'm going to write an example, then we're going to process it together. Find the maximum value of z for the first plus 7y if x must be greater than or equal to 0, y must be greater than or equal to 0, y must be less than or greater than or equal to, sorry, y must be less than or equal to 7, x must be less than or equal to 6, and y must be less than or equal to negative x plus 9. So these are our conditions, and that is a function that you want to find the maximum value of that function. So here are the parameters, here are the boundaries, and you want the maximum for that. Okay, so how do we approach this? Well, the first thing we do is we find the common area for all 5 inequalities. What area satisfies all 5 sets of inequalities? So that's step 1. Step 2, find the vertices, the corners of the shape that is formed that covers the common area. Then at those vertices, find what the coordinates of x and y are. Use those values of x and y to see which one gives you the maximum for z. That's a mouthful. That's a lot I've just said. So let's go through the process step by step. First thing, we'd like to graph these inequalities and find the common area. And then we take it from there. Okay, so x is greater than or equal to 0. Y must be greater than or equal to 0. So again, we are only focusing on the first quadrant, nothing but the first quadrant. We're not interested in quadrant 2, quadrant 3, or quadrant 4. What we're interested in is the first quadrant, where x is positive and y is positive. So that takes care of this, takes care of that. Then the next thing is that y must be less than or equal to 7. So y cannot be more than 7. So we can go here. So let's see, if we go to okay. So y is, so this is 2, 4, 6, 8, and this is going to be 9 right here. Okay, so y is less than or equal to 7. So this is 7 right here. So this is the line y equal to this is the line y equal to 7. y is equal to 7, between 6 and 8, then x must be less than or equal to 6. So we could go here. So this is going to be the line. So it's a solid line. So I can go and not dotted, but solid. So this is a line, x equal to 6. So far so good. So now we need to deal with this inequality here. So we have this boundary here, this boundary here, this boundary here, and this boundary here. So somewhere in here is going to be our solution set. So now we have to consider this portion right here. Y is less than or equal to negative x plus 9. So this 9 represents your y-intercept, okay? And the negative slope means that you go across 1 and you come down 1. So it's going to be something to this effect. And it's a solid line, and it's going to be going with a negative slope, so it's going to be something so this is your graph of y equal to negative x plus 9. So let's see if we could shade the area. So we're going to shade to the right of this, above this, below this, to the left of this, and this is less than or equal to, and below this. So our shaded area is going to be this area, satisfies all 5 conditions. You don't have to go beyond this line because it stops at this line right here. It says x must be less than or equal to 6, so you can't go over here. You stop at 6. It says y must be less than or equal to 7. You can't go above 7. You have to stop at 7. So this is the area that satisfies what you're looking for. Now, you need to find what makes, where in this area you'll find z as a maximum. And this is where you have to listen carefully. For linear programming, your minimum or maximum, notice it could be the minimum or the maximum, they are always located at one of the vertices. That's a vertex, that's a vertex, that's a vertex, that's a vertex. So there are 5 vertices, singular vertex, plural vertices. So we need to know the coordinates of these 5 points. Okay, so this one is easy. So maybe we could just label them to make it easy. So let's call this A, call this B, call this C, call this D, call this E. So some of these points are very easy to locate. A is the point 0, 0. That's easy. B is the point 0, 7. C, we're going to have to work out C. So let's keep C for a little bit. D, we're going to have to work out D. Keep that for a little bit. But E, we know that E is going to be 6, 0. So D, E is 6, 0. D we don't know. C we don't know. These we have to calculate. It's going to be where this line crosses this line. Okay? This line, we know that y is 7. But the question is, what is x when y is 7? Okay? And then here, we know that x is 6. But the question is, what is y when x is 6? So we need to work those out. So let's get to work. Okay. what's the intersection of y equal to 7 and y equal to negative 7 minus 9? Okay, so therefore we solve negative x plus 9 is equal to 7. So negative x is equal to negative 2. So x has to be 2 when y is 7. So the point C is 2, 7. What about this one? X has to be 6. So what is y when x is 6? So y is equal to negative 6 plus 9. Y is equal to 3. So this one is going to be 3, 6. Okay? And now we have obtained all 5 vertices. 1, 2, 3, 4, 5. And now we're getting ready to determine the maximum, which is the ultimate objective. What is the maximum? And what we learned in linear programming is that your maximum or your minimum will always be at one of the vertices. Somewhere at one of these 5 corners will be your maximum or your minimum. So what we'll have to do now is that we'll have to test the function z equal to 4x plus 7y using these values for x and y, but x and y, x and y, x and y, x and y. So according to this one, 4 times 0 is 0, 7 times 0 is 0, so this is going to be 0. According to this one, 4 times 0 is 0, 7 times y, 7 times 7 is 49. According to this one, 4 times 2 is 8, 7 times 7 is 49, and 8, we're getting 57. According to this one, 4 times 3 is 12, 7 times 6 is 42, 42 plus 12 is 54. And according to this one, 4 times 6 is 24, 7 times 0 is 0. This gives me 24. So of these 5 vertices, of these 5 sets of x and y values, which one gave us a maximum value for z? And the answer is the point C. So the maximum is z is equal to 57, and that is obtained when x is 2 and y is 7. So you have just been introduced to linear programming. That is what linear programming is. It's really a college concept, and many people will see it in college like economics and what have you, but that's basically what it is. You graph, find the vertices, plug in the values for the function that you're testing, and extract the maximum if that's what you're looking for. And of course, in this case, if you are asked for the minimum would occur at the origin, right here, 0, 0. That's where the minimum would occur. Got it? Okay, let's try another one, and then we can seal it. One more. Okay. So I've just listed the constraints horizontally, just for convenience. Again, the important thing here is we're in the first quadrant. Again, just the first quadrant. Okay? So let's go. Okay, so y is less than or equal to x plus 1. So our slope, so our point of intersection, not point, so your your y-intercept is 1, your slope is 1. So this is 1, 2, 3, 4, 5. Uh-oh. I want to go to -3, but I'll have to do something else. So let's go. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, good. So the first one, y is less than or equal to x plus 1. So 1 is our y-intercept. Go across 1, go up 1. These are 2 points. And now we can draw. And it's a solid line. So we can go. Okay. This is the graph y equal to x plus 1. And the next one, did I have 1, 2, 3? Oh, I missed one. X plus 1. Then why am I missing? And then another one is 4y plus x less than or equal to 10. Okay, this one is more involved. So let's go for this now. Okay. So now we go. Y is greater than or equal to x minus 3. Okay, so what I'll do is when x is 2, y is going to be -1. When x is 3, y is 0. So let's go here. When x is 4, y is 1. When x is 5, y is 2. Okay. Now we have so this is our line y minus x equal to -3. Okay. So now we need one more graph, and that's the graph 4y plus x less than or equal to 10. So if we were to rewrite this, which is ugly, we would have 4y is less than or equal to -x plus 10. Okay? I think I'm going to simplify it so that it's not as ugly as this. Let me give it a different degree, just to make it easy. Let's go 2y plus x is less than or equal to 6. Let's try that. So then in this case, we now end up with 1 is less than or equal to a half x plus 3. Negative a half x plus 3. So we end up with y-intercept is 3, and slope is -1/2. So you go across 2 and down 1. Go across 2, you're down 1. Okay, here we go. So let's see if we could get this together now. It is less, so we are in this corner. For this one, the first one, we said it's less than, so we're shading below. For this one, it says less than, so we're shading below. And for this one, we're shading above. So the graph is gonna be in this section right here. So that's your graph. So what are your points? The points are, your vertices are A, B, C, D, and E. A, B, C, D, and E. So let's see if we could make a little space. Yeah, don't use up so much. So this is okay. Okay, so what are our vertices? A, 0, 0. B is 0, 1. C, we're going to have to calculate where these two lines intersect. E, we know is going to be, E is going to be 3, 0. 3, 0. So these two must be calculated. Okay, so for the first one, C, we're looking at y is less than or equal to -1/2x plus 3, and the other line is this line that says y minus x is greater than or equal to 8. Okay. This line here, okay, so for this one right here, so x plus 1 must be equal to -1/2x plus 3. So add this to this side, we end up with 3 over 2x equal to 3. So therefore, x is equal to 2. So when x is 2, if x is 2, y is going to be 2 plus 1 is 3. So this one is going to be 2, 3. Let's go to this one right here. This one is again this line right here and this one. Y minus x, so therefore put the x over here. We have x minus 3 equal to -1/2x plus 3. Add this to this over here, we end up with 3 over 2x equal to 6. So therefore, x is equal to 4. When x is 4, y is equal to +1. So it's going to be 4, 1. So now we need to evaluate our function z equal to 2x plus 4y and see which one of them gives us a maximum. So let's repeat. What we did, we graphed the inequalities, found the common area, we calculated or we determined the 5 vertices, 1, 2, 3, 4, 5. We determined what the 5 vertices are, and now we're going to evaluate the function z equal to 12x plus 4y based on these x and y values, x and y values, x and y values. Okay, so for this one, is 2 times 0 plus 4 times 0, that's 0. For this one, it's 2 times 0 plus 4 times y, so this is just 4. For this one, 2 times 2 is 4, 4 times 3 is 12, 12 plus 4 is 16. For this one, 2 times 4 is 8, plus 1 is 9. For this one, 2 times 3 is 6, plus 0 is 6. So where is our maximum? Our maximum is at the point C that has x as 2, y as 3, and the maximum value equal to 16. So welcome to the world of linear programming that incorporates inequalities or systems of inequalities. And we have obtained maximum. And in other situations where the graph doesn't have a vertex at the origin, you will find that you can get a minimum that is not 0. Okay? It all depends on what function you're calculating. But the process to get a minimum is the same process. And then all you have to do is, instead of taking the one that gives you the biggest value, you take the one that gives you the smallest value. So if you were asked for the minimum is 0. But that's too trivial in this case. Okay? So that's that for inequalities and systems of inequalities, plus your intro into linear programming. I trust that this was interesting, that you learned some things, and I'm hoping that as we continue, that the progression will keep up. I'm looking forward to dealing with sequences and series. But before we do that, I think I'm going to spend a little time solving systems of equations. Systems of equations, 2 equations, and systems of 3 equations. And then we'll get into series and sequences. Okay? On behalf of the Brosis Foundation, I thank you for joining us in a session dealing with systems of inequalities with an introduction to linear programming. We trust that you will enjoy the rest of the day, and also that you'll join us again as we learn together, sponsored by the Brosis Foundation. Enjoy the day.